Welcome back. So, after the last lecture, there was one big question. What was the question? The question was if we plot the lambda m c with respect to root c for strong electrolyte, we are getting this kind of plot, a straight line, okay, with the intercept. Now, at c tends to 0, at c tends to 0, if we extrapolate at 0, that is c tends to 0, your lambda mc molar conductance becomes lambda m0. Now this lambda m0 is known as limiting molar conductance. Limiting molar conductance. Hmm? Acha. Now this limiting molar conductance is can be calculated for the strong electrolyte. Hmm? Okay. So let's talk about the strong electrolytes here. Okay. Now we need to assume few things. Okay. Before moving into that constant C tends to 0 region. So what happens at C tends to 0? Number one, first thing what we will assume that the solution is a complete dilute solution. Is a complete dilute solution. Okay. Number two, what we can assume? Okay, complete dilute solution. Number two, at zero concentration, C tends to 0, your electrolytes are 100% sorry, dissociated. Electrolytes are 100% dissociated. Okay. Number three, we can assume the interionic forces that is between the cation anion, cation. Okay. The interionic forces zero. So these three things we have to assume at concentration tends to zero, and that region is known as infinite dilution. Okay? Infinite dilution. Okay. Now, this infinite dilution, when Kohlrausch was a person, scientist, so Kohlrausch thought about this infinite dilution and he gave a law, and that law is known as law of independent, yes, independent migration, law of independent migration of ions, law of independent migration of ions at infinite dilution. Okay, at infinite dilution, he gave this law, and this law is known as Kohlrausch's law. Cohl. Let's take the spelling. Kohlrausch. Kohlrausch's law. Okay, very important. One of my favorite law. Okay. So what he said the ions will behave independently. Don't care. Hmm? Now, if they behave independently, then whatever their charge or the conductivity will be there, that will depend on their number, right? If there are two ions present or the four ions present, so that four ions will behave independently. So their charge, if their charge, let's say plus 2, so 4 ion will have total charge what? 8 plus 2 into 4, right? So what we can say, the total lambda m0 is equal to lambda 0 of the cation multiplied by n plus, which is the number of cations, plus lambda 0 of the negative is the n minus. The n minus n plus is the number of cations and N minus is number of anions, right? N plus is the number of cations and N minus is the number of anions. So this is the molar conductivity which we talked about. Okay. Now what happens to the equivalent conductance at infinite dilution? The equivalent conductance, basically this is a number. The equivalent conductance depends on the charge, right? So what I will put here 1 by Z plus, which is the charge of the cation multiplied by lambda plus at infinite dilution, and Z 1 by Z minus by lambda 0 minus. Okay. Now if this is possible that these two cases are the numerical. If these two cases are possible, okay, and let's assume that what Kohlrausch is telling is true, and if possible, yes, this equation arises, this is fine. But if the ions really behave independently, okay, if the ions really behave independently, then can we do one thing here? Okay, what is that? Here, what we can do is basically this is the lambda m at your infinite dilution, and this is the lambda, let's say at concentration. Let's say this is the lambda at particular concentration. Let's say at this concentration, you have this particular lambda m. If I talk about, so if I compare this lambda and this lambda, can I get a value? Yes, indeed I will get. We will get alpha, which is equal to lambda by lambda m by lambda m0. Okay, lambda m0. Okay, lambda mc by lambda m0. This alpha is known as dissociation constant. Known as dissociation constant. Okay, it's known as the dissociation constant. This you can calculate from here. Okay, and we know that for your okay, acha. Now when I'm saying the law of independent migration ions, and I'm assuming that ions are migrating independently. So can I do one thing here at lambda m, very low lambda m value? Okay. So for let's say if I take two solutions, let's say I'm taking a KCl solution and I am taking a NaCl solution, and both solutions are at infinite dilution. Both solutions are at infinite dilution. And other way I can, let's take sodium sulfate solution and potassium potassium sulfate solution. K2SO4. Okay, this solution. If you take, yes. Now what are the possibilities here? Now if I calculate, if I add these two solutions, or I can subtract these two solutions. So from here what I will get, lambda K plus lambda Cl minus minus lambda Na plus minus lambda Cl minus, right? 1 1 1 1 1. And if in this case also what I will get here, lambda Na plus, okay, plus lambda SO4 minus 2 minus lambda K plus minus lambda SO4 minus 2, right? Now this will cancel out and this will cancel out. Okay, let's take this half balance. Okay, now put 2 minus. Now can you see here one thing? This is also lambda K plus minus lambda Na minus. This is also lambda Na plus and lambda K plus. I'm sorry. we something is wrong. Mm, okay, let's A2SO4 plus Na2SO4. Okay, this is Na plus, this is K plus, that's fine. If we minus, so what we will get? We get lambda K plus lambda Na minus lambda K plus lambda Na. Okay, so that means by using these two solutions, not actually, theoretically, if we know the lambda 0 of KCl and lambda 0 of NaCl, if we take the difference, that difference will be equal to the lambda 0 of potassium sulfate and lambda 0 of sodium sulfate. So application of infinite dilution is this thing where your ions when independently migrate, okay, when the ions independently migrate, it does not depend where it came from. It does not depend which electrolyte it is from. Okay, because in this case also you are getting K plus minus Na plus, and in this case also you are getting K plus minus Na plus. So does not matter where your these solutions, these ions are coming from. Okay, this is the huge advantage for infinitely diluted solutions, and this is what Kohlrausch was telling to us. Yes, is telling us. Hmm? Okay, now uh, if we talk about that for the weak electrolytes, if we talk about the weak electrolytes, so dissociation constant, when we are defining the word dissociation constant, as I said, let's define it. So for the weak electrolyte, so we cannot calculate the lambda zero, right? But we have to know there is a few ways we can do that. How we can do that? We can calculate this alpha. This is lambda by lambda zero. Okay. And from your acid base chapter, you know one thing, for the weak electrolytes, the dissociation constant. Okay, so this is the degree of dissociation. Okay, and dissociation constant K, which is equal to what? Okay, I will not derive this. Equal to what? C alpha square divided by 1 minus alpha, right? Now, what we can write in place of alpha, C is the concentration C by lambda m 0 C square divided by 1 minus lambda C by lambda m 0, right? This equation we will get. Hmm? Okay, if we rearrange, what we will get? C lambda C m by lambda m0 square multiplied by lambda m0 divided by lambda m0 minus lambda mc. Okay, correct me if I'm wrong. Okay, so by this equation, if you know that equilibrium, your dissociation constant, if you know this lambda c value from the graph, and if you know the c value, so you will be easily able to calculate the lambda m0 for the weak electrolyte. So this is the application of Kohlrausch law, is the lambda m0 for weak electrolyte. I'm taking my word back because as I said that time that weak electrolytes you cannot calculate lambda zero. I was wrong. Yes, indeed you can calculate the lambda zero for the weak electrolytes, but you have to do it a separate way. But for that you need to know the dissociation constant. Hmm? For that you need to know the dissociation constant. Okay. Now Uh, okay. What else is there? Okay. So if I talk about now, let's say if this solution, okay, this part is done. If we talk about the NaCl solution, NaCl solution, in case what happens in case of NaCl? In case of NaCl, your for your N plus is basically the number of cations and N minus is number of anions, right? Now, if for NaCl, if this is one, this is also one. Yeah, if I am assume N plus is one, and mm, okay, and what is your Z plus? Z plus is also one. Here also Z plus is also one. Z minus is also one, right? Now for Al2SO4 whole 3, N plus, let's assume 1. Okay, let N plus, let's assume 1. Hmm? So in this case, what is your Z plus? 3. Aluminium is plus the charge. And what is the N minus here? N minus, let's say 1, if I am assuming. So Z minus is, okay. So this is the, now what you can do, if you know the lambda values of the corresponding ions, then you can easily calculate the lambda m0. Hmm? Okay. Acha. Uh, wait. Something is wrong. Here the number of aluminum is true, 2. And here the number of is 3. No, now it's 3, 2, 2. Ah, 2. Not well actually. Hmm. And anything else? So till then, your this Kohlrausch's law part is over. So the conductance part, the electrolysis part, the electrochemical cell nurse equation, numericals that I will discuss later. Things are over. So and next, what we will discuss after this is your the application of the this electrochemistry in case of different titration like acid base titration. Okay, where you do this titration using the electrochemical method. Okay. Then I will go to the different kinds of batteries. Okay, fuel cells, corrosions. Okay, then different batteries are there, calomel batteries are there. So that part we will discuss one by one. And after that, I will take one more lecture which will be based on which where I will cover for each examples, each cases, I will do the numerical problems. So till then, in the next video. So okay, so bye. Thank you.